What's up, everybody? This is Matt Brown with another IoT hacking video. Today I have another security camera in my hands. Today this is the well-known brand Hanwha. Specifically, this is a WiseNet modeled camera, and we'll take a look at the specifics in a minute. But before we dive in, my name is Matt Brown. I am an IoT pen tester by day, and on this YouTube channel, in my free time, we tear apart devices like this and really see how they work on the inside and see how a IoT bug hunter or pen tester would actually take one of these devices apart and start to look for security vulnerabilities in these devices. Now, this camera is very interesting, and it's going to be actually the start of a series that we do on commercial off-the-shelf cameras that are targeted not at the residential market, but again, the C in that acronym, the commercial market, right? These are big boy cameras. They have all the features that a very large commercial security, where you have a security guard posted at a desk, is going to want, and this is the camera model we're looking at. Now, here we can even see on the company website, before we dive into the specifics of this model of device, what's kind of cool is they've got a cybersecurity link here. So I found that this is actually pretty interesting and is actually going to direct some of our analysis, because it's always fun to challenge the claims that are made, especially when it comes to cybersecurity marketing. So here we can see, okay, yeah, you guys take security really seriously, you know, best practices, that's awesome. So here's some of the claims, kind of the baseline claims they're making. And this is not specific to one product or another. And so you kind of assume that this is a policy that's across all their devices. And so hopefully they will apply to this device that we'll test, but we will find out. Okay, complex password policy. Yeah. Not going to get popped by Mariah by having super easy creds. All right. HTTP/HTTPS. So I assume they mean that, like, they're redirecting. They redirect up to HTTPS, or at least they make it available. That's all fine and good. No backdoors via Telnet and SSH. So they only do non-Telnet and SSH backdoors, right? Is that what that means? I don't think so. But and the last two are really interesting, and I think this is going to guide some of our reverse engineering after we get past some of the initial device analysis and the firmware extraction. Is they have this claim that the firmware is encrypted. Now, they don't give a lot of details here, and they just say application encrypted firmware. So does that mean that it's encrypted at rest on the flash, all of it? And it's using some kind of keys and trust zone, doing some cool things like that? Maybe not. We'll find out. And then they also say database encryption. Database encryption, whatever that means. I don't know if that's specifically in the context of like a DVR and NVR device where there's, you know, streaming video from a camera that's stored on, you know, big hard drives. Maybe that's what they're getting at, that video data is encrypted at rest or something like that, but that's another claim that we can look at. Now, this is going to guide some of our reverse engineering right here. So encrypted firmware, I think I understand what they mean by this, which is like, it doesn't mean anything, because when we go back to the product page here, so we can see all the cool features that this camera has, but down here we can actually download a copy of the latest firmware file here, and I've actually already done that over here. So I have this zip file, which we will just run on zip. And so, yeah, a bunch of PDFs, release notes, stuff we don't care about. So here's the actual firmware file right here, this image file. And so we're just going to run binwalk on it. And you'll notice that it identifies right away at the 0 byte offset, right at the beginning of the file, that it's OpenSSL encrypted, and it identifies the salt, right? And if you haven't seen what this looks like in kind of like a hex editor before, let's go ahead and take a look at that now. I'm just going to use XXD. And so here we can see that there's a bunch of binary data in this file But right at the front, we see it say salted and then underscore. And so if you've ever looked at files that OpenSSL encrypts before, you will notice, you'll recognize this format, right? This is a pretty common output this file would be from using OpenSSL to do file-based encryption. So a fun reverse engineering project that we will have later on throughout this video series is determining what the key is, right? Is there some password that gets generated in firmware and then it does a password-based key derivation function? Or is the key just hard-coded itself? Or is it obfuscated in some kind of binary? That's always a fun reverse engineering challenge to go down the rabbit hole and figure out, okay, there's a key somewhere on the device because it needs it to decrypt the firmware when you upload it, probably via the web interface, right? So this will be a fun quest that we will go on later, not in this video. Because first, we're going to go over to our bench and take a look at the hardware. Let's do that right here. Okay, so on the desk today, I have, as you can see, we have already removed the guts of the camera out of the shell just for convenience so that I can get at all of the fun stuff. So right now I have it unplugged, and you'll see there's a bunch of these wires that come off. There's, one that's labeled mic, one that's labeled speaker, right? So there's clearly, two-way audio. I think we saw that on the website, that's a feature of this camera. This is some kind of an arming, for having like an external alarm that would trip or something like that. And then we have Ethernet, and so obviously this device is power over Ethernet, like almost all cameras of this kind of form factor, again, in the commercial space, because then you don't have to run two wires, right? You just have to run one wire. So up here, when we get into that, I just have a very simple from TP-Link. This is a PoE injector, so I have just regular old Ethernet that'll be on my network, and then this will have power injected into it so it can power our device. So with that, let's start taking a look at our camera. And let's zoom in. So here we see the one side of the camera, and this is the absolute not interesting side, except for what we're actually going to eventually find out today. So I spent a lot of time looking for, kind of the obvious UART interfaces. That's the first thing I will always want to find. I want to identify the flash chip. That's like identify flash chip, find UART. That's what you want to do. So let's flip this over, and I'll be gentle not to like break this ribbon cable on the other side. And we'll try to get this in focus. So there's some really interesting stuff here, right? So first of all, right off the bat, if I can get that correct in the light there, you'll see that the main CPU chip is branded as a WiseNet Hanwha, piece of silicon here. So that is super, super interesting here. And then obviously we have our kind of standard layout here of a Linux-based device, right? We have a CPU, we have our DRAM chips, and then over here we have the storage chip, which is actually going to be interesting. So let's look at that a little bit closer, and we may want to use the microscope for this part. We'll see. We'll see if we can get you guys a good image. Actually, no, this is good. So you can see here that there are a number of markings on this flash chip. Actually, yeah, let's use the microscope. So right here, you can see that one of the sets of markings on the chip is very faded. And so let me get this into focus for you. And I have to just hold it at the right angle, and you'll kind of see it start to materialize there. So you can see the number that is actually important for this chipset, it starts right here. So we can see 27, and we can see what is hard for you guys to see in the camera, but what definitely looks like a J, if I remember correctly. Now I'm even having a hard time seeing it. So this is a very interesting form factor of chip. It's not an eMMC chip, right? It's not large enough, and it's it's definitely not an eMMC chip. So this is a BGA 63 pin package, and so we're gonna have fun in the next video because I think this is the first time I've ever encountered a package like this. So I'll get to use a new adapter for the first time in this video, or in the next video. So that's good to note, and we're gonna find out more about this flash chip today because I was not able to identify really the flash chip by any of the markings on here, and gosh, it's really hard to get a good angle on this. But okay, there we go. You can kind of see. So it says JS right here, JS. Unless I'm just really blind. But that JS, it turns out, is either not right or this is like some quasi knockoff or copy of a different chip. And we will get some information from the UART on that. All right, let's go back to the bench. So now what we're going to do is, now obviously we need to find UART. So I looked all over on this thing. So the long story short, I looked over here because you can see right here we have a micro USB interface. So I'm thinking like, oh, okay, maybe I plug this into my computer and it shows up as a UART interface, like some devices have those debug interfaces built in. That was not the case. I, checked some of these other interfaces, these external wires, made sure that exit out of the camera to make sure that that's not it. And then the only unpopulated connector I had left was this. Where there is I don't have anything else off camera here. You can see this other little plastic enclosure thing that I have here, but there is no ribbon cable that I ever removed from here. So that is really interesting because a lot of times with UART, you'll just have like 4 or 5, pins on a connector somewhere. But here we have a whole ribbon cable. So, but this is potentially a debug ribbon cable. A lot of devices, especially small form factor devices, for development and debugging, they'll actually have a whole bunch of debug resources on an external PCB, and they'll just connect it via a ribbon cable like this, which makes things easier sometimes. So let's go ahead and we're going to start to probe around here, and we're going to do that under the scope just because it's a little nicer. All right, so we've got our little connector here. There we go. Let's get us in focus. Wrong way. There we go. And we're going to turn on our overlay here. And I'm going to make sure that we go into continuity mode. All right. So now we're going to we're just going to confirm first of all that I can, connect to ground, that I can find a good ground plane. So over here, there's these grounded out things. And so, and an SD card thing. Okay, cool. So I've got ground somewhere. That's great. So now, let's see, is there ground anywhere on here? Okay, pin 3. Pin, whatever that is. All right, so there's a couple pins. Pin 3 is kind of a distinct pin there. Now what we're going to do is we are going to go ahead and we're going to plug in our device. I am going to just do this delicately. Okay, so we're going to plug in our device and we're going to switch to voltage mode here. And we're now going to probe for voltages across these pins. All right, nothing there. Pin 2. Nothing on pin 2. Oh, I had it turned off. I thought I turned it on. I'm like, wait a minute. I'm pretty sure there's supposed to be voltages on some of those. All right, nothing. Nothing. We know that's ground. And okay, we have 3.3 volts on pin 4 here. Pin 5 has some voltage. Ooh, look at that. Doesn't that look like UART? That's going all over the place. So, spoiler alert, yeah, that's probably it. But you can see on an engagement like this, if I encountered a interface like this, that's this non-standard, that is this custom, I'm going to want to characterize the voltages. So I literally would have a pad of paper next to my desk, and I would be like, all right, pin 1, that was oscillating between 3.3 and 0, or pin 5, it holds at 3.3 or something like that, right? I would kind of go around and see, you can see other pins down here, further down, that are holding at 3.3 volts. And I would just characterize these pins, and that would help me when I move on to the next step. So what we're going to do next is we're going to hook up our logic analyzer. So we're just going to move away from that for a minute. And so we're going to discuss the setup of our logic analyzer. So I do have my Soli logic analyzer here, and we're going to just connect up one of our little pogo pins here, and we're going to connect it up to that pin that was clearly oscillating in its voltage there. So what we're going to do is we need to connect that, and then we need to also connect to ground. So any of these little black wires here on the logic analyzer, we're just going to, again, I don't need to have a pogo pin connect to anything, so I'm just going to connect this little alligator clip over here. I know that's ground. And then this, under the microscope, we will place on the right spot. So let's go and do that. And we don't need our multimeter anymore. Okay, it was on 1, 2, 3, 4. Oh gosh, was it on 4 or 5? Okay, there we go. We got it. And so now what we're going to do is we're going to come over here to the Soli Logic 2 program, and we're going to, set up our device. We only need one digital channel enabled. That's fine. And so we're setting it for 3.3 volts. That sample rate is just fine. Doesn't need to be that high. And we're going to go ahead and we're going to power the device off. And we're going to start. Let it go away. I'm just going to zoom out here. We're going to, oh. No, we're, spoiler alert. All right, we're going to delete that. You didn't see that. You have to stop the capture. All right, so obviously you can see data bouncing around here, and we already we already decoded it because I already had that set up. But I'm going to show you how we would go about decoding data like this. So the first thing I'm going to do, just kind of scroll in here at the beginning. Okay, this looks like some good data here. And so you can see here, the logic analyzer software actually kind of helps us out here. So if I find one of the small symbols here, right, what I think might be one symbol, it might be one one bit, right? So right here, you can see that it says I can't point to. Okay, so it's gonna be over here on the screen when I do it here. Oh, now it's on the other side. Okay, now it's on the right side. It's on the right side of the screen, up there. So you see that it says width 115.42 kilohertz, right? So that is suspiciously close to the kind of the default baud rate of 115/200, right? It's just a little bit off. So what we can do now is we can go to analyzers and we can go async serial, and we can enter in a baud rate of 115/200. That's kind of the default for a Linux device. And then the input channel, we only have one channel here right now. And leave all these other things as standard. Again, if it failed to decode, then I would maybe go back here and twiddle and fiddle with some of these. But the first thing I would always try to change is the baud rate. That's most common. That's like usually going to be the thing you have to figure out. So there we go, and you can see that it's decoding all of this data in all of this ASCII here. And so here we clearly have the boot log of the device. And so now what we're going to do is now we know that this is a standard UART interface. So we have found the transmit pin of the device, and now we need to hook up a regular old UART to USB 3.3 volt cable, and we need to find the receive pin so we can transmit data and type into this console. So let's go back to the bench and get that set up. So now we don't need the logic analyzer anymore, but we're actually going to use its little interface here. So we are going to use two of these now to connect to the two pins that we need to connect to. So I'll probably, like come at it from this side. We'll come at the two pins that way. And so now what we need to do is we need to connect up this to my cable, which is over here. So I have my 3.3 volt UART cable, and so I have ground, which I'm just going to connect up to this alligator clip like we did before. And then I'm going to connect the receive up to the yellow wire on the Soli on the probe. So yellow is going to be what we want to be receiving from the board's transmit, and then we want to connect this up the opposite way. So we need to, oh gosh, yeah. Okay, let's go back and get these situated. All right, there we go. And this is so funny because you will be able to know because you're watching the video, but I literally just forgot I forgot which pin is which. So we're gonna go back over here, clear this out, PicoCon. There we go. And we're going to make sure, okay, I'm on pin 4. No. Okay. So pin 5 is transmit. So we're going to guess that pin 4 is our receive. So we're gonna try to connect up to pin 4 over here. Don't cross the streams. Come on, man. There we go. Okay, so those should be, and now we can test by hitting enter, and we have confirmed that we have now found the receive pin on the board, and we properly connected our transmit pin of our UART cable to it. So, very, very cool stuff. Let's actually, now you can see we have a prompt. Let's see if we can get into the UART bootloader. Spoiler alert, we're not gonna be able to do that. Okay. I'm gonna click all the, it says that enter a key. I'm clicking all the keys, okay? It doesn't accept input at this part of the boot process. Later on down, you'll see like all of my hitting enter there and all the good that did. Not any good. But we get some really valuable information out of these boot logs that is going to help us when we do the chip off on that device. And because it actually identifies the chip, and so let's go find that. It's like when it prints out the table. Here we go. Again, okay. This is a total like freebie aside thing. This partition table that the boot logs print out, this is always super helpful. When I'm on an IoT pen test, I will grab this, and this is like going to be the first thing that I put in my notes, because later on when I go to dump the firmware, I may or may not Binwalk may or may not be able to figure out what all these different file systems are, right? But if I have this partition table well defined like this, then I can just use DD to copy out the different partitions and have them very systematically, and then I can try to unpack them all individually, and I can target which one I really care about. So this is always super helpful. And here I'm getting, again, just incredibly important information about the NAND flash chip. And here you can see that it is a Hynix H27. That's not an H on the chip. That's definitely like a J. And so these chips, you'll see this all the time if you do a lot of firmware extractions off of chips like this, where there'll be one chip that is effectively the same across a bunch of different models, right? Like one manufacturer will make a chip, and then someone else will be like, hey, as a kind of a cheaper option, I should manufacture a similar chip that matches all the same specs and is interchangeable with the brand name one, right? And then I can undercut them in the market and have this product placement thing. So, but this chip here and this identifier here, I was able to just go here and then, so excuse my RDP madness here, but I can go into my software here. Again, I always like to go check in my firmware reading software before I go and do a chip off, and then find out that, oh, my reader doesn't support it. So here you can see that I just went into the search and I pasted the whole thing. And sometimes you have to hit backspace off of this because it won't like match the full string. So I just have to hit backspace, and you can see here that it does have this chip here, and it has the two different models for it. So it has a TSOP 48. So those are the ones where all the pins are exposed on the two sides of the chip. And then we have the one that we have on our board, which is this FBGA 63. And so here it tells us, this is helpful. So it says adapter compatible with T56. So I do have a adapter for that, for my firmware reader, that should work in the next video when we go ahead and perform the firmware extraction, because I'm super excited. I want to go test all the claims. And so this is going to be a set of videos, not just on this camera, but other ones on commercial, off-the-shelf security cameras. We're maybe even going to release some tools around specifically testing these kind of devices and like the OnVIF standard. So please hit subscribe if you're interested in this content. Thank you for watching. Share it with your friends. Have a good day.